Welcome back to the FTTM podcast, your guide to getting the right product to the market at the right time. This week, we are going to focus on FTTM planning, how to execute to achieve right time.
It is great to be back. And, just to make sure we're all on the same page, FTTM, of course, stands for fast time to market.
Right.
That's what every company is chasing. But the key thing we're going to unpack today is that fast doesn't mean rushed. I mean, that's a huge distinction.
Absolutely. Rushed is pure panic. Fast is all about strategy. And today, we're going to be drilling down into a concept we touched on back in episode 8, scheduling innovation.
Yeah, but we're going much deeper this time.
Oh, way deeper. We're really looking at, the central paradox of building anything new today. How in the world do you put a deadline on a breakthrough that hasn't happened yet?
That is the million-dollar question, isn't it? Or in some of the cases from the lateral works research we'll be looking at, it's literally the billion-dollar question.
It really is. The single biggest mistake we see teams make, especially when they're working on some kind of breakthrough tech, is assuming they'll get it right the first time.
The right first time fantasy. It's so seductive.
It is. It's like your entire corporate culture is built on this idea that you're not allowed to be wrong.
And if you look at a standard project plan, a real one from a big company, it's just a straight line. It's A to B to C.
No loops, no detours.
No room for error. It just assumes right from day one that the team somehow knows exactly how to solve problems that, by definition, have never been solved before.
Which, when you say it out loud like that, it just sounds absurd.
It is absurd.
But we do it. We do it because the alternative, admitting you don't know, feels terrifying.
It feels like you're going to get fired. But the solution, and this is what we're pulling from the lateral works research and lateral works best practices today, is actually about leaning into that uncertainty. It's about using something called learning cycles.
Learning cycles. It might sound a bit academic at first, but when you get into it, it's incredibly practical. It's this mix of math, a little bit of psychology, and honestly, just having the nerve to schedule failure right into your plan.
And that's really the hook, isn't it? How do you schedule something when you don't even know what the solution looks like? How do you plan for the unknown?
That's what we're here to figure out.
Yeah.
So let's start with some context. Why is this such a huge problem right now? Why are engineering teams feeling this pressure more than ever before?
To really get it, you kind of have to look back at the history of R&D. The lateral works research, particularly a paper called Innovation Can't Be Predicted, lays it out really well.
Okay, so we're talking about how things used to be versus the pressure cooker we're in today.
Exactly. If you rewind to, say, before the 1990s, the corporate world was pretty neatly divided. You had research, and over here you had development.
Two completely separate things.
Two different planets, really. Research was the ivory tower.
The lab coats and beakers.
Pretty much. It was happening in corporate labs, Bell Labs, Xerox, PRC, places like that. And it was totally unscheduled. The timeline was just, it'll be ready when it's ready.
You can't put a due date on an epiphany, right?
You can't. And they had that luxury. The cycle times were long. We're talking 5 to 7 years to get a basic technology from a concept in a lab to something that could be handed off.
And that handoff went to the development teams, the NPD, new product development folks.
Right. And by the time NPD got their hands on it, the basic science was done. The R part was finished. The D part was about, packaging it up, figuring out how to manufacture it, designing the plastic case.
They were dealing with knowns, so they could have schedules, they could have budgets.
Because the physics already worked.
Yeah.
But then the 90s hit, and the internet and the speed of Silicon Valley, everything accelerated.
The great merge, as the research calls it.
Yeah. Companies looked at those 5 to 7 year timelines and just said, we can't compete like this. We'll be out of business. So R&D budgets got slashed, labs were shut down, and the two functions were smashed together.
So the research scientists and the product engineers are suddenly sitting in the same cubicle farm.
And the timeline just collapsed. It went from years to, like you said, maybe 10 to 15 months.
In some industries, it's even crazier. The lateral works research points to storage systems where cycle times dropped below 6 months.
Less than 6 months. Think about that.
Yeah.
That's barely enough time to get your parts ordered from a supplier, let alone invent a new recording head technology.
And that's the core of the problem we're facing today.
That's the crux of it. Teams now have to do fundamental research, the stuff that used to take years in a lab while the product development clock is ticking. You're inventing the engine while the car's already in a race.
This brings us to what the research calls the engineer's pushback. I've been in these meetings. I've seen this happen. You ask a lead engineer, okay, when is this new feature going to be done?
and you just see them cross their arms. Their whole body language changes.
Yeah, and they say, I can't tell you. And they're not trying to be difficult.
No, they're being brutally honest. What they're really saying is, I can't tell you when I'll find the solution because I don't even know why the current version is failing yet.
It's that loop. You have to know the why to figure out the how, and only then can you predict the when.
Right. And because management needs a date, any date, this is where you get the wild-ass guess. The WAG.
The manager keeps pushing, just give me a number. And the engineer finally caves and says, 3 weeks.
Just knowing in their gut, it could easily be 3 months.
And then that 3-week number gets baked into the master schedule. It becomes fact. And when they miss it, which they always do, everyone acts shocked and disappointed.
This is where the lateral works best practices come in with a pretty hard line. It's understandable why it happens, but from a business perspective, it is completely unacceptable.
You can't go to your investors and say, well, our Q3 earnings depend on whether Sarah in the RF lab has a moment of inspiration next Tuesday.
It doesn't work that way. So not planning isn't an option. The core assertion here, the big idea, is that you can manage and predict innovation. But, and this is the whole point, you have to change what you're measuring.
So you stop measuring how close you are to being done.
And you start measuring how much you're learning.
Which brings us right to the core concept. Learning cycles.
This is the heartbeat of it all. This is the mechanism that lets you plan the unknown.
There's a mantra in one of the Lateral Works papers that I love. It's so simple, but it's so radical for most corporate cultures. It says, learning means failing. Failing means learning. Failing quickly equals learning quickly.
It just flips the whole script on its head, doesn't it?
Yeah.
In most companies, failure is, it's a dirty word.
Oh, it's the worst thing. If your test fails, you're behind schedule. You just wasted a bunch of money on a prototype. You're in the hot seat.
Right, so people hide their failures. They massage the data. They call it a partial success or inconclusive results.
Anything but it didn't work.
But in the learning cycle model, failure is actually the goal. Or, maybe a better way to put it, is that getting the failure out of the way is the goal. A learning cycle is just a structured experiment.
Plan, do, check, act. It's the scientific method.
It is the scientific method, but with a stopwatch attached. The key metric for the team shouldn't be, did we get it right? It should be, how many cycles did we run this week?
Because every cycle that fails is a path you now know is wrong.
Yes. If you think there are, say, 10 possible ways to solve a problem, and you know 9 of them are dead ends, your job is to find those 9 dead ends as fast as humanly possible.
This also changes the job of management, of the leadership team. The research talks about the steering committee. Their job is no longer just to ask, are we on schedule?
Their job is to be a snowplow, to clear the path so the team can run cycles faster. The central economic principle for them has to be, the cost of delay is almost always greater than the cost of investment.
Let's unpack that for a second. Cost of delay versus cost of investment.
Okay, so imagine a simple scenario. You have a team of 5 expensive engineers, and they're all stuck. They can't run their next test because they're waiting on a custom part from the machine shop.
A familiar story.
The shop says it's a 5-day lead time. But they also say if you pay a $5,000 expedite fee, you can have it tomorrow morning.
Okay, so the traditional manager looks at their departmental budget and says, $5,000 for one part. Absolutely not. We'll wait the 5 days.
That's thinking only about the cost of investment. They're saving $5,000. But they're ignoring the cost of delay.
Right. What's the cost of those 4 days they're waiting?
Let's say this product, when it launches, is projected to make $100,000 in profit per day. By waiting 4 days, you just pushed your launch date back by 4 days. You didn't save $5,000. You lost $400,000 in profit.
When you put it that way, it's a terrible trade.
It's a catastrophic trade. But it happens constantly because the engineering manager's budget is separate from the company's profit and loss statement. FTTM-focused leaders understand this. Their mantra is spend to save a day.
So you're provisioning for speed. You're buying the extra tools, the faster computers, the better materials.
If the team needs the other oscilloscope, you don't make them share one. You buy another one. If they need to fly an expert in from Switzerland for a day, you book the flight. You never, ever let the team be idle because they're waiting for a resource.
But even with all the resources in the world, you still have to fight that internal right first-time culture. The Lateral Works research points out that a lot of companies, if you look closely, have literally 0 learning cycles in their official schedules.
It's what's called a success-oriented schedule. It's a plan that assumes every single step will work perfectly the first time. The first prototype will work. The first software compile will be bug-free.
It's just a work of fiction.
It's totally delusional. But managers create them because if they actually put a line item in the plan that says redesign circuit board after first test fails, it looks like they're planning to fail. It looks like they're padding the schedule.
Someone from finance will say, wait, why do you need 4 weeks for testing? It only takes 3 days to run the actual test sequence.
And the answer is because the first 5 times we run it, it's going to fail in new and exciting ways, Bob. The hard truth is this. For any genuinely hard problem, it is almost never solved on the first try. So planning for 0 cycles is actually guaranteeing a schedule slip.
Whereas planning for, say, 5 cycles makes the schedule realistic.
It makes it robust. It makes it honest.
Okay, so this is the philosophy. How do we make it practical? How do we put a number on it? Because I can't go to my VP and say we need some learning cycles. I have to put a date in the project plan.
This is the magic. This is where we get into the math.
Yeah.
It's a method from the research attributed to folks like T.J. Rogers and Tony Alvarez. It's how you put a number on the unknown.
I love this because it takes something that feels fuzzy and subjective and makes it quantitative.
It starts with a simple act of categorization. Even if you don't know the solution, you and the team have a pretty good feel for the problem itself. You know how scared you are of it.
You know the degree of difficulty.
Exactly. So you categorize every major unknown into one of 3 buckets: easy, hard, or difficult.
And difficult isn't just, this is annoying. Difficult means bleeding edge. It means we are genuinely not sure if this is possible with today's technology.
That's the one. Easy is something like we're changing a resistor value or the color of the plastic. Hard is we're pushing the performance, but it's based on an architecture we've used before. Difficult is true invention, new to the world stuff.
Okay, so you've got your buckets. Now what?
Now, you assign a baseline number of learning cycles to each bucket based on historical data and team experience. The lateral works research gives a good starting point.
What are the numbers?
For an easy problem, you budget for 1 to 2 learning cycles. For a hard one, you budget 3 to 5 cycles. And for a difficult, bleeding edge problem, you budget 6 to 8 cycles.
Okay, so now I have a number of tries. I can say this is a hard problem, so we think it will take us, let's say, 5 attempts. But how do I turn 5 attempts into a duration on a schedule?
You have to define the duration of one single complete cycle for that type of problem. And this is really important. A cycle isn't just the time you spend thinking, it's the whole loop.
So it's design the experiment, get the materials, build the test fixture, run the test, gather the data, and then analyze the data. The whole thing.
The whole thing, end to end. Let's say for a particular type of hardware problem, the team decides one full cycle takes about 15 days.
Okay, 15 days per cycle, and we said it's a hard problem.
So we're budgeting for 5 cycles.
So you just do the math. 5 cycles times 15 days per cycle is 75 days.
75 days. That's the number you put in the Gantt chart for that task.
And you can already hear the project manager screaming, 75 days! But you told me the test only takes 2 days to run.
And the engineer's response has to be, the test takes 2 days. Finding a version that passes the test is a gauging. Hard problem that we estimate will take 5 cycles. The duration is 75 days.
That's a brave conversation to have.
It is, but think about the alternative, the old way. You let the PM put 15 days in the schedule, the right first-time guess.
And then it actually takes 5 cycles, 75 days.
Now you're 60 days late. 60 days, you've missed the market window, your competitor just launched. The whole project is in crisis mode.
But with the learning cycle plan, if you put 75 days in the schedule from the start,
and you get really lucky and the team nails it on the second try in 30 days.
Then you're 45 days ahead of schedule. You're a hero.
You're a hero. You've just pulled in the schedule. You have all this buffer time you can use somewhere else. It completely changes the dynamic. It replaces a random, fear-based guess with a quantified, risk-managed estimate.
It also changes the psychology for the team on the ground.
Massively. If the first test fails, they don't go into a panic. They don't feel like they failed. They just say, okay, that was cycle 1. We learned that approach A doesn't work. On to cycle 2. They are executing the plan, not failing the plan.
But this requires a different way of tracking progress. If the schedule has a 75-day block and 40 days have gone by and we still don't have a working part, how does a manager know if the team is on track or just spinning their wheels?
That is the perfect question, and it leads us right into the next critical concept. The difference between learning milestones and product milestones.
Okay. Traditional project management loves product milestones. Things like prototype assembled, alpha units delivered, first customer ship.
And those are fine. They're great for the 90% of the project that's just standard execution. But for that 10% that is true innovation, they are worse than useless. They're dangerous.
Because you can't have a milestone for prototype assembled if the core technology is, literally on fire on the test bench.
You got it. For the innovation part of your project, the milestone question has to change. It can't be, what did we build? It has to be, what did we learn?
The Lateral Works research has a case study about this that is just...
Yeah.
It's a perfect, if terrifying, example, the story of the burning component.
Oh, yeah, this one is a classic. It's an engineer's worst nightmare. So this client had a system, and it had two key components sitting right next to each other.
Okay.
And the performance requirement was insane. One of the components had to heat up to 2,000 degrees Fahrenheit.
That's, what, like the temperature of lava?
Basically, yeah. But here's the crazy part. It only had to be at that temperature for 1 nanosecond. Just an impossibly short pulse of intense heat.
Okay, so super hot, super fast. What was the issue?
The issue was that every single time they fired that 1 nanosecond pulse, the component next to it would just vaporize. It would be completely destroyed.
And because it was happening in a nanosecond, they had no way to see what was going on.
No way at all. It was too fast for any high-speed camera, too fast for any sensor they had. All they could do was run the test, open up the chamber, and find a little pile of ash where the second component used to be. No data, just catastrophic failure over and over.
And in the meantime, you've got a manager with a product milestone schedule asking them, so when are those first samples going to be ready for the big trade show?
Exactly. The team was being driven crazy by these product sample milestones. They were trying to build the full integrated product. But every time they did, they just destroyed the evidence of the failure. They were burning through time and money, and the schedule was slipping by months.
So what was the pivot? How did they break the cycle?
They finally took a step back and realized they were tracking the wrong thing. They completely changed their plan and moved to learning milestones. They accepted that the goal, for now, wasn't to build a working device. The goal was to understand the failure mechanism.
So they actually rewrote the project schedule.
Threw the old one out. The new schedule had milestones that looked totally different. Milestone 1 was successfully install instrumentation to capture thermal data at the nanosecond level.
They weren't even trying to fix the problem yet. They were just trying to see it.
They were just trying to get a picture of the crime scene. Milestone 2 was isolate the primary heat transfer path. Is it conduction, convection, or radiation? Milestone 3 was test effectiveness of insulation material A.
They were scheduling the science.
They were scheduling the learning. And once they focused on that, they figured out how to slow down the event, how to capture the data. And it turned out the solution was actually pretty straightforward once they understood the physics.
But they never would have gotten there if they kept chasing that product complete milestone.
Never. The lesson is so clear. You cannot schedule hardware assembly when the fundamental physics of your system doesn't work yet. You have to schedule the discovery process first.
This makes so much sense, but it also implies a different way of planning a whole project. If your first few months are full of these unpredictable learning cycles, how can you possibly create a detailed plan for what you'll be doing in month 12 or month 18?
The short answer is you can't. And the strategic answer is you shouldn't even try. This gets us into a technique called refresh planning.
I've seen those project plans, these beautiful, color-coded, massive Gantt charts that stretch out for 2 years and claim to know what some engineer will be doing on a Tuesday afternoon in 2026.
They're works of art, and they are complete fiction. There's a story in the research about a client whose project plan had 3,500 individual tasks just for week 1.
3,500 tasks. How do you even track that? That's just paralysis.
It is the ultimate illusion of control. The management team felt great because they had this incredibly detailed plan, but this was a high innovation project. The fundamental architecture was still in flux.
So the very first thing they learned in week 1
invalidated the other 3,499 tasks. The whole plan had to be thrown out. It was a colossal waste of everyone's time.
So what's the alternative? What is refresh planning? I really like the analogy the research uses for this.
The driving in the fog analogy. It's perfect.
Yeah, explain that.
Okay, so imagine you're on a road trip, driving from New York to Los Angeles. You know your ultimate destination. That's your high-level project goal. That's your macro plan.
But you're driving through dense fog and you can only see, say, 50 feet in front of your car.
That 50 feet is your micro plan. You plan that stretch of road in excruciating detail. You know every pothole, every slight curve where you need to tap the brakes.
So in a project, the immediate future, the next week or two, that's your micro plan.
Exactly. For the very next learning cycle, you break it down into daily tasks. Who's doing what equipment do we need, what are the specific experiments. It's high resolution.
But you don't try to plan the road in Ohio when you're still in Pennsylvania.
No, because you can't see it yet. For learning cycles, #2, #3, and #4, you just leave them as big, chunky summary blocks in your schedule. Cycle 2, 15 days. No more detail than that.
Because the results of cycle 1 will determine what you even do in cycle 2.
Right. If cycle 1 is a huge success, maybe you get to skip cycle 2 entirely. If cycle 1 is a disaster and you learn you're on the completely wrong track, cycle 2 might be a total redesign.
So you refresh the plan continuously.
Every week, you have a meeting where the team gets together and says, okay, we just drove another 50 feet. The fog has lifted a little. What can we see now? And then you plan the next 50 feet in detail. You are constantly refining your long-term plan based on the immediate reality.
It's just so much more adaptive. It acknowledges that you get smarter as you go.
Why would you want to be locked into a decision you made 6 months ago when you were, by definition, dumber than you are today?
No, there's a specific psychological trap that teams fall into when their project has a mix of this really hard, innovative stuff and a lot of standard, easy stuff.
Yes. Section 6. Isolating innovation. This is all about the 10-90 rule.
So the idea here, which comes from people like Preston Smith and Donald Reinertson, is that even in the most breakthrough project, most of the work is actually pretty boring.
That's right. About 90% of the work is stuff your organization has done 100 times before. Designing the power supply, laying out the main circuit board, writing the standard drivers, creating the packaging.
And then there's the 10%. That's the magic, the one new sensor, the crazy new algorithm, the one piece of physics that's never been done before.
And the trap is all psychological. The whole team looks at that 10%, what they call the long pole in the tent, and they get completely fixated on it. They think, wow, that quantum physics problem is going to take the PhDs a year to figure out.
And because of that, they think, well, I've got plenty of time to work on my part, the simple power supply, there's no rush.
Why should I kill myself to get the chassis design done by next week? The scientists are going to be stuck on that hard problem for months anyway. So all the management attention, all the team meetings, everything revolves around that 10%.
And in the background, that 90% of easy work is just crawling along at a snail's pace.
And then the inevitable happens. I have seen this play out so many times. The science team gets lucky. They have a brilliant breakthrough 6 months earlier than anyone expected. The 10% is solved.
And everyone celebrates. High fives all around.
Champagne and everything. And then the project lead turns to the rest of the team and says, great. Where's the rest of the product? Where's the circuit board? Where's the power supply?
And the engineer says, I haven't really started that yet. I honestly thought you guys would take way longer.
And just like that, the easy, boring 90% stuff has become the critical path holding up the entire project.
You've solved the impossible, but you can't ship because you don't have a plastic box to put it in. It's just tragic.
It is. So the lateral work's best practice here is crystal clear. You have to isolate and focus. You draw a hard boundary around that 10% innovation.
You treat it like its own separate project.
Exactly. You isolate it from the main development path. You give it its own dedicated Tiger team. And most importantly, you start it as early as possible. Give that hard problem the longest possible runway to get solved.
And you run the 90% stuff in parallel.
In parallel. And here's the crucial instruction you give to that team. You must execute your work as if the innovation is already finished and successful. You build the rest of the car with a perfectly engine-shaped hole in it, assuming that engine will show up on time.
So that the moment the innovation is ready, you can just drop it in and you're ready to go.
You don't let the uncertainty of the 10% infect the certainty of the 90%.
But what about the other side of that? What happens when a team gets greedy and tries to innovate on too many things at once?
Well, then you get the too many innovations case study. This is such a great cautionary tale.
Because we all want our new product to be the best at everything, right? The fastest chip, the newest manufacturing process, the slickest software.
That's what this team tried to do. They decided to innovate on 4 major fronts at the same time.
Okay, what were they?
They had a brand new IC design, a new manufacturing process to build that chip, a completely new firmware architecture, and a new industrial design concept all at once.
That's 4 huge independent variables. And in engineering, when you multiply the probabilities of success for multiple new things,
the total probability approaches zero very, very quickly.
Mm-hmm.
And that's what happened. The project just ground to a halt. Every time a prototype failed, they had no idea why. Was it a bug in the new chip? Was it a flaw in the new manufacturing process? Was it a firmware problem?
It's impossible to debug. A tangled mess of unknowns.
They were just drowning, so they had to make a really tough, pragmatic decision. They basically had to kill some of their darlings.
They had to choose which innovations actually mattered the most.
They did. They decided the most critical innovation was the new IC design. So they reverted to an older, proven, much more stable manufacturing process. They went back to using existing firmware modules wherever they could. They simplified everything else to focus all their energy on that one chip.
But the research mentions they took a yield hit by doing that. The old manufacturing process wasn't as efficient.
That's right. The shiny new process promised a higher yield, meaning fewer bad chips per wafer. By using the old, reliable process, they had to accept a 2% lower yield.
Which, in the semiconductor world, a 2% yield loss can mean millions of dollars. The finance people must have been having a heart attack.
Oh, I'm sure they were initially.
Yeah.
But this is where you have to do the FTTM math. By simplifying the project, they broke through the gridlock. They figured out the problems with the chip, and they got the product to market 10 months earlier than they would have if they'd stuck with all 4 innovations.
10 months early.
Now, this wasn't just any product. This was a blockbuster. The Lateral Works research says this thing was projected to generate $4 million in profit per day.
Wait, say that again? 4 million?
$4 million in profit, not revenue.
Per day?
So 10 months. There's about 300 days. You do the math. 300 days times $4 million a day.
That's $1.2 billion?
$1.2 billion in extra profit they captured because they launched 10 months early.
Okay, so now you compare that $1.2 billion gain to the cost of losing 2% of their chips.
It's not even a comparison.
Yeah.
It's a rounding error. It's pocket change. They would have lost $1 billion chasing the pennies they'd save from a slightly better yield.
That example is just staggering. It perfectly illustrates that time getting to market is often the most valuable and most expensive resource you have.
And it shows you have to be willing to make strategic trades. You might have to trade features or cost, or in this case, manufacturing yield, in order to buy yourself time.
Which requires a certain kind of thinking. It's not linear.
It's not. It requires lateral thinking. Which brings us to our last big topic. Lateral thinking and system architecture.
This goes back to Edward de Bono's work, right? The idea of not just digging the same hole deeper, but trying to start a new hole somewhere else.
Exactly. And in a big company, this usually means you have to have a way to challenge the sacred cows.
Every project has them. These baked-in assumptions. We must use this supplier. The product has to be under 200 grams. The decision was made 3 years ago to use this software platform.
And the problem is that those decisions were usually made by someone very senior, a VP, a director, the founder of the company.
So a junior engineer asking, why are we still doing that, feels like a really risky thing to do.
It feels like a career-limiting move. Who are you to question the VP's wisdom? So the team just silently works around these old, bad constraints because nobody has the courage to speak up.
So the lateral works approach suggests you need to formalize the process of challenging these things.
You have to make it safe. You schedule a specific review, a challenge session, where the explicit purpose is to question old assumptions. The question on the agenda is, are the reasons we made this decision in 2023 still valid today in 2026?
By making it part of the official process, you take the personal risk out of it. It's not insubordination, you're just doing your job.
Right. And what you often find is that the solution to these really tough cross-functional problems isn't inside any one department. It's in the white space between them.
The interfaces.
That's where innovation hides. There's another great example in the research about a complex semiconductor project. They were stuck. They couldn't hit their performance targets.
And every team was working as hard as they could.
They were. The chip design team was optimizing their logic gates. The manufacturing team was tweaking their process parameters. The software team was optimizing their code. Everyone was a hero inside their own silo.
But the overall product still wasn't working.
Because the solution wasn't in any of the silos. It was in the trade-off between them. It turned out that if the software team made their code a little bit more complex, which they didn't want to do,
Of course not. It's more work for them.
it would allow the hardware team to dramatically simplify the chip architecture, which in turn would solve the problem the manufacturing team was having with yield.
But the director of software is never going to volunteer for that. His job is to make his team's life easier, not harder.
That's the problem. Silos optimize for themselves. They want to hit their own targets, stay within their own budget. This is why you absolutely need the role of a system architect.
Someone whose job isn't to manage a function, but to manage the entire system.
And manage the trade-offs. The system architect is part engineer, part diplomat, part horse trader.
They trade complexity between teams.
That's a perfect way to put it. Their job is to look at the whole product and say, okay, I am going to make the software team's life 10% harder because it makes the manufacturing team's life 50% easier. And that trade saves the company 3 months and $20 million.
They optimize for the whole, not for the parts.
And that person needs to have real authority to make those cross-functional calls stick. Without a strong system architect, all you have is a collection of silos, each doing their best, but accidentally suboptimizing the final product into failure.
Wow. We have covered a huge amount of ground today. I mean, from the history of R&D to project planning math to psychology to org charts.
And it is a lot. But if you take a step back, it all connects. There's a single thread running through all of it.
It's honesty, isn't it?
It's radical honesty. It's about being brutally honest about what you know and even more honest about what you don't know.
Okay, let's try to boil this all down. Let's recap the biggest takeaways for everyone listening.
Number one has to be, don't guess estimate cycles. Stop using wild-ass guesses. Categorize your unknowns as easy, hard, or difficult, and do the math to create a realistic, risk-managed duration.
Number 2, fail fast to learn fast. Change your milestones for the innovative parts of your project. The goal isn't what did we build, it's what did we learn. Remember that burning component.
Number 3, isolate the 10%. Find that single piece of scary innovation, draw a circle around it, give it a dedicated team, and start it early. And then run the other 90% of standard work in parallel as if that innovation is already guaranteed to succeed.
And number 4, refresh planning. Drive in the fog. Plan the immediate future in high detail, but keep the long-term plan flexible and chunky. Update it constantly as you learn more.
And maybe a final bonus one. Empower a system architect to break down those silos and manage the white space.
It's a really comprehensive way of looking at product development, and it's not easy. I can just imagine how hard it is to be the first person in a company to stand up and present a schedule that has 8 weeks of failure built into it.
It takes real courage. But as we saw with that $1.2 billion example, the reward for being realistic and getting to market on time is astronomical.
It really is. So, here's a final provocative thought for everyone to take away. Go look at the project plan for the most important project you're working on right now. If that schedule looks perfect, if it's a clean, straight line from today until your launch date, with no loops, no buffers, no learning cycles baked in,
then the plan is a lie.
and you're probably already late. You just don't know it yet. Real confidence doesn't come from a perfect-looking plan that pretends nothing will go wrong. Real confidence comes from having a plan that anticipates the struggle and is built to overcome it.
Planning for the unknown is the highest form of control you can have.
Thanks for listening. Make sure to tune in next week, where we will dive deeper into key practices of FTTM teams.